Hello and welcome. Today we're going to look at running some finite element analysis in a batch using a combination of FreeCAD and some Python scripting. FreeCAD, if you don't know it, it's CAD, it's a computer-aided design package. It has a lot of workbenches. It can do part design, it can do some finite element analysis, and it's really easy to script through Python. So the aim of today is to try and model this part and to pull it from these two boundaries, these two holes, and try and make the section as small as possible and see what the effect of making it smaller is, and trying to see what the optimal cross section would be if we were to manufacture. To do so, we're going to model the part in FreeCAD. We're going to set FreeCAD up so that it can very easily change that dimension for us. We're going to set up a simple analysis in FreeCAD, and then we're going to write a little bit of Python to do it automatically, but completely outside of FreeCAD. So you don't even have to have a monitor. You can run this on a server, and you can see the results of all your analyses afterwards. If you're interested, I'll put the code and the FreeCAD files in the description on my GitHub. And yeah, let's start. We are going to switch to the part design workbench if you haven't yet done so, and then let's save this straight away as parametric. So first thing I want to do is I want to create a new body. So this button here, it could be in a different position on your FreeCAD installation. We are going to then create a new sketch. So first of all, I want to show the axes and planes. You do it with space on FreeCAD if you haven't used it too much. So I want to create a new sketch. And I want to create it on any plane really, but in this case I'm going to use the XY plane. And I'm going to create the base shape, which is quite simple. I can create it as a slot over constraint by default, but if you flag auto remove redundant, it is 4 degrees of freedom under constraint, which means we can move this point into these. So that's 3, and then the 4th one is the width. So at the moment this is quite unpredictable. As you saw, the thing is flickering everywhere. So the first thing I want to do is I want to block this on the this point onto the horizontal line. Next thing I want to do is I want to make the shape symmetric, so I can use the symmetry constraint. I need to select point, and axes. Now we're left with 2 degrees of freedom. One is the height and one is the width. And we can constrain these to the dimensions we want. In this case, I want 100 millimeters between centers and 22 millimeter outside radius of 44 mil. So let's set the length, the distance between these 2 points first, horizontally, and I'm gonna give this 100 millimeters, and then constrain the diameter. So, and in this case it picks up the radius, it's fine. I want to set this as 22 millimeter radius. I want to draw the holes straight away. As you see, the outer bit turned green because it's fully constrained. I can't move it. Now I've created 2 extra circles and I want to make them equal, and I want to make them 25mm diameter. So pick this up again. Again, you can use whatever dimensions you want. So I want to use this as a base for my shape. The shape will be 10mm thick. So I want to create a pad, and we can find the pad in the geometric tools here. The pad will be 10mm thick, but I want it to be symmetric to the XY plane. So I have generated the pad, and then I want to create the cutout, which is going to make this part narrower, and that's where all the parametric features will be. Do this in a slightly convoluted way. It might seem convoluted, but it will make sense when you accidentally left the sketch. It will make sense when you see why I'm doing this, but for now I'm going to create this cutout by using 2 circles. They will be identical and they will be symmetric. So equal and symmetry around the horizontal axis. So 2 degrees of freedom, one is the distance and one is the radius. So I'll fix the radius first. You can run the analysis by changing any parameter. In this case, I've chosen to change the cutout width, but and keep the diameter fixed. But you can do the opposite and let me know in the comments if you try and what happens. So I'm going to set the diameter to 125mm, and I'm not going to change it again. So 125. So I'll show you what happens. This is under constraint, so this is a free parameter. I'll show you what this does to the shape, and I'm going to create a pocket. I'm going to do the pocket as an infinite pocket, so I don't accidentally, if I want to vary the thickness, then I don't accidentally end up cutting only a part of it. And I'm going to do it both sides. Now, I am also going to go back in the sketch, which is under constraint, and I am going to fix the distance between these 2 parts. To do so, I can do it in a couple of different ways. I can probably set a point to be at the same time on the vertical axis, so coincident, and on the circle. And then I can set the vertical distance between these 2. And that's going to fully define the sketch. So if I come out, now the sketch is fully defined. So I want this to vary between, say, 20 and 30mm, or 15 and 30mm. One thing that is really useful to do is to give it a name. So I'm going to give this the name of cutout width. This is really important because you don't want to end up trying to refer to things like constraint 8, constraint 25. If one constraint gets deleted and gets replaced, then maybe your constraint changes name, and you can't really trust this name to not vary. When you rename it, 2 things will happen. One is it will that name will stay. Also, if you click on Sketch, you open constraints, this the constraint that you have just created will come out of the unnamed block. So on unnamed, you'll see all the constraints. So one thing I can do straight from here is I can set this to 5mm, and the parameter changes straight away. I can set this to 30mm, and again, this is pretty much instantaneous. I'm going to rename the sketch for the same reason as I renamed the dimension. So cut out sketch. The reason why I'm doing this is because you can then really easily script this in Python, and I'll show you how in a second. So to show the Python console, you have to go on View, then Panels, and then Python console. And this is a Python interactive console. It's Python 3.8.10. This will be important if you want to write your own script, because you have to match the Python version that FreeCAD comes with. That's fairly easy to do, and anyway, with virtual environments these days. The first thing we're going to do is we're going to try and find the sketch, and one way to do it, so FreeCAD has an object called app. Then you look for the current document, because there could be many. So I could go to active document. It's got autocomplete. It's really handy, especially if you're exploring and you don't know how an object is constructed. The document has a function that's called getObject, and it takes a string, and the string can be the name of the object. So if I try and get the object called pocket, was to assign this to a variable called pocket, and then you can inspect pocket, and you can look for the sketches, which in this case are called profiles. So the profile is a list in this case. Inside the profile, we want to access the cutout variable. So we call this sketch. Let's call this target sketch. Inside target sketch, we can loop over the constraint. So if you go target sketch dot constraints, there's a few constraints. This is I think a list of constraints. We want to find a constraint that is called the name that we gave it, but you can't see it from here. So we want to loop over all the constraints, and this code again you can find on the GitHub, and then if constraint dot name equals the name we gave it, and that was cutout width. And then we break. So now we know which constraint is the one that we want. In this case, its number is in position 8. So the sketch has another method. So target sketch dot, and it has a method that's called setDatum or setDatum. You give it the index, and then you give it the value. So I want to set this to 5mm. Nothing happened, but the sketch has been flagged for recalculating, and you can recalculate from here just by doing recompute, and you have to recompute the pocket as well. Or, and let's set this again to 25. You can do this in code just by doing app.activeDocument.recompute. So these two, now that you have the edge index, you don't have to care about it anymore. You can always use these two functions to dynamically change the size of the geometry you want to change. I'm going to hit save, and I am also going to add, I'm just going to add a little round, and I'm not going to make it too big because this has the potential to break your model. But in this case, I can probably safely leave it at 10 millimeters for now. So the next step is to prepare this for the analysis. Before I jump into running the analysis, what I'm thinking is, can I simplify this model? Because especially if you have to run 100 of variations of this, then if your analysis can be 10 times quicker, you may go from taking a day to run a family of 100 or 1,000 analyses, and then down to, you know, a tenth of that time. And that can save you a lot of time, especially if something goes wrong, or if you have to make a reasonably quick decision. So what I'm going to do is I'm going to set this up to split the part in, to chop the part out from this . Okay, so the advantage of doing this, at least in my opinion, is you can roll back, again using space, you can roll back in time, and you can have a part that is fully ready for 3D printing, manufacturing, creating a 2D drawing, sending out as a step file for manufacturing. And then the symmetry features are just on top of it, and you can suppress them or unsuppress them as you want. The advantage is, again, you're not modeling a quarter and then you have to do mirrors, or if it has a more complicated part, it doesn't really lend itself to then readapting a part for what was its original function. Okay, so the geometric part is nearly finished. I just wanted to test one last time the code to change the datum's dimension. So I'm going to set this to 5, and I'm going to recompute the architect document dot recompute active document is, there we go. So that works. We're happy. We're just going to set this back to say 15 and leave it for now. The next thing we're going to do is we're going to set up the finite element analysis. So we can go directly to the FEA workbench in FreeCAD, and it's called FEM for finite element method. First thing you want to do is you want to create a analysis container. Just going to leave it called analysis. What it does, it automatically creates a solver object is using Calculix as a finite element solver. Don't touch anything for now. We won't need to touch anything, but if you know what you're doing, you can. Then we need to do a few things. We need to mesh the part. We need to create boundary conditions, and we need to assign a material. It kind of helps you that these things are sort of left to right in the FEM workbench. So the first thing is we're gonna assign a material for a solid part, and just going from here, we can select, say, a random aluminium. There's an aluminium generic material. It's got, again, a generic intensity, a generic Young modulus, and some thermal parameters. So we're going to add the part as a solid. So we're going to click, and it's picked it up, and it's assigned the material to the geometry. We then click OK. The material has been assigned. We need to create boundary conditions. So luckily, having the symmetry faces makes constraining this quite easy. The boundary conditions are in this menu. So you can have boundary conditions in terms of displacement here, and then forces out here. So we want to create a generic displacement. We want to create, let's say, this face first, and we're going to select both and add them to the constraint. What we so for a symmetric constraint, what it means is all the points in this plane, they can't move along y, because if they move along y, they would enter the rest of the part, but of course they can't because it's symmetric. But they are free to move in vertical, as in z and in x. So we are going to set the displacement along y to be fixed to 0, and all the other displacement will be free. We don't care about rotations because these are only used for shell elements. So click OK. Some arrows appear that indicate I am supporting the part on this plane. I want to rename it straight away before I forget, and I'll call it ysim BC, as in boundary condition. I'll do the same for this face, which is a symmetry along the x-axis. So generic boundary condition, add, and then fix the x displacement and leave all the others free. And this is xsim boundary condition, and I want to do the same for the this other plane. So I want to add this face. This face is along the z-axis, so on the xy plane. So xy are free and z is fixed. And that's the last one. Don't worry about the direction of these. I'm just going to rename it as ZSimBC. All of these boundary conditions are bidirectional, so you can't, it's not resting on a plane, it can't move from the plane. Next thing we want to do is we want to apply a force, and we're going to apply it to this 8 of a hole, a quarter of a hole actually. So to apply a force, we apply a constraint force, we select the face, and then we also have to select the direction. So we're going to set this as 5 kilonewtons. The direction that we want is along the x-axis, so we can select either the axis or the plane. I'm going to select the plane, and as you can see, the force is going in, which is wrong. I want it to go out, so I have to flag reverse direction. Save. Might want to rename it, so load. Again, you can parameterize these as well if you feel so inclined. But so we have boundary conditions, we have material, we have set the load. The next and last step before running the analysis will be to create a mesh. So as a mesher, you can use either NetGen, which is built in with Calculix, or you can use Gmesh as an external mesher. I'm going to use NetGen for this, but it's not available. It's not available from any of the analysis parts, but what you have to do is you have to click on the body you want to mesh in the tree, not just on the body, on the bit of the tree that you want the mesh to be referring to. So you click on FEA mesh from shape, and we're just going to set a maximum size of 1 millimeter, so we get 5 elements along the thickness. It's not necessary in this case, but let's just do it. We click apply, and a mesh will appear. It's tetrahedral, it's horrific, but for this case, I'm not going to spend any time trying to make the mesh better. The mesh is available here. And then we can run first analysis in the model. I'll save, and then I'll go to Solver CCX Tools, double click. What FreeCAD does is it writes an input file for the solver. I can show you what it looks like. It's not pretty. If you click on edit.imp file, you can see that it's basically defining all the nodes, the node coordinates, and then try and find LSet. There we go. So it's going to define elements using these nodes. Type of element is C3D10, is a 10 node tetrahedral element. So it's a second order tetrahedral element. All the it's first defining an element set, and it says I'm going to assign the material to this part. It's going to define the material lower down, and then it's going to set the displacement constraint to the nodes that belong to the faces that we've selected. Again, 1, 2, and 3, and then lower down is going to define the constraints, directions, and that happens, I think, here. Yes. So where it sets boundary is, it says the nodes that belong to this are constrained in direction 2. These are constrained in direction 1. These are constrained in direction 3. If you're not familiar with numbered directions in finite elements, it's normally the x is 1, y is 2, and z is 3. And then it defines a set of concentrated loads so that the sum of the nodes is equal to the total load that we specified. And then that's it. It's going to ask for some results. So this hasn't run yet, but what we need to do is we need to run the solver against the input file, and this happens automatically when you click on Run Calculix. It's going to take a few seconds. Mind you, this might be slower because I'm also running OBS to record my screen. On your machine, this might run quicker. So it's running about 15 seconds, and then it's loading the results, and it's finished. The results appear here as a CCX results object. What I'll do is I'll hide the mesh by pressing space. I'll also hide the boundary conditions. And what I'll do is I'll add to this results object a pipeline, a post-processing pipeline. This isn't going to be needed in our script, but it's useful to see if the analysis has worked. So at the moment this is empty. We have to tell it what we want to see. And I want to see, as a surface, I want to see the, for example, the von Mises stress. And that's showing the most stressed area is the that part of the hole. And the stress is about 200, sorry, this is in the way, I'm going to move it, 229 megapascals in this case. So where this is useful, while this is useful to just say, oh, this is stressed this much, remember the objective was to determine what the size of this cutout would be optimal to reach a target stress. And if you know the target stress, you can then run the analyses, the parametric study, so that you find out what that dimension is. Another thing you can do from results pipeline is you can add a, so I'm just going to run the, just show the surface, but I'm also going to add a deformed object. So I'm going to add a warp filter based on displacement, and I'm going to color it as displacement. Increase the warp to 10. So this is showing how the new surface is deformed compared to the original one, and it's small. So 140 nanometers. If you hide results pipeline, you can see the warp vector. You can also fiddle around with transparency to show the original shape. You can just go for outline if you only want to see the outline, and then you have to play around again with some transparency to see the original shape underneath it. Anyway, so this is all nice. But really what we want to do here is we want to script this analysis, and we want to run a lot of these analyses at once. So how do we do it? And I really like to run this headless because I might want to just throw this on a high performance computing server somewhere else. I want to run this on a machine that I don't have a monitor attached to. Whilst I am trying to figure out how to get the model screenshots out, one way we are doing this is just by, say, picking the maximum von Mises stress and the maximum displacement. Again, this is just an example. Then you can change the script to extract whatever parameters you want. You can extract the probability distribution of stress. You can get the principal stresses. If you're dealing with different materials, you can get the Tresca stress, or you can get deformations, or whatever you need to get out. So I'm just going to open the code that you can get from my GitHub. And so really quickly, I think the easiest way to run this is by using virtual environments. I'm using pipenv. The pip file has all of the requirements, and the only thing is specifying Python 3.8.10 because it needs to match the FreeCAD version. If your FreeCAD version is different from FreeCAD 0.20, which is what I'm running now, you may need to change this, and this may break things, so your mileage may vary. So you have to do a couple of things. The first thing is you need to tell where FreeCAD is, and so that basically Python can find it. This I'm not sure is necessary, but I was having some trouble before. It's just telling the operating system where to find some more libraries in the FreeCAD folder structure. And then just some imports. I'm using pandas just for convenience to store the results, and I'm using Plotly for plotting. Again, you can use whatever you fancy. You can use Matplotlib, you can use Seaborn, you can use Knock Yourself Out. The settings that you want to change are, so you want to point the script to the right file. You want to change the object name. So this is running off the other model, which is identical to the one I just created. The only thing is I named the constraint spacing. The object name is pocket. The results file needs to match the Calculix results object that you have in the tree. So this, in my case, is ccx_results, and it needs to match the solver name as well. So that's the first object that we created, is solver ccx tools. Again, if you change it, remember to change it in the script as well. And then here I'm just specifying the parameter range for a sweep. So I'm going to make it a little bit easier first. So I'm going to run maybe 3 analyses, so at 15, 20, 25 millimeters. This is just initializing pandas data frame, and then the bulk of the script starts here. So we are using the object FreeCAD that we imported. VS Code doesn't really find it because we are importing it with by appending it to the path. If you have a solution for this, let me know and I'll update my instructions. And then, as we did before, we are we're looping over the range that we defined. And then I'm calling this function that I wrote. It's called FreeCAD change param. And what it does is it finds the sketch as we did in the script before. and then it finds the constraint index, it sets it, and it just updates the document. So once we've done that, we can create and run an FEA analysis. And this is, again, scriptable. First, you find the solver object. It's the same as we did when we were finding the pocket. In this case, I'm using solver name, which is solver CCX tools in this case. I'm cleaning up the results if there are any. And I'm going to reset the FEA. I'm going to update it to update the mesh. I'm going to check if everything is fine. I really should put some error handling here, but I haven't yet. And then run the FEA. And then return the results as an object. In this case is the results that we have specified as CCX underscore results. So that's where we exit the FEA, and then I just add the results to a table, to a data frame. And in this case, I'm using I'm adding both the von Mises, the maximum von Mises stress across the whole mesh, and then also the maximum displacement from the original shape. I'm also saving the runtime just because. And then at the end, when it's done all of the analyses, I'm going to plot the results. I'm not going to bore you on this, but I'm also going to show the data frame. So I'm going to run this by running pipenv run FEA-parametric, FEA-parametric.py. FreeCAD is going to give us some output that we never requested. Again, if you know how to suppress this, let me know. And the analysis is finished. We get some results, and we get a couple of seconds, 3 seconds runtime. But what we get also is a plot. And Plotly opens a browser window, and we can see how we have, so on the left axis, the maximum von Mises that goes from 220, 201, 183 as we refine, as we make the cutout a bit thicker, and the displacement behaves the same, so it decreases as we make the part fatter. I'm going to go back to VS Code, and what I'm going to do is I'm going to quickly run a few more slightly more refined analysis. I'm just going to set this up as a step of 2. I'm going to run this again, and I'm going to fast forward through this. So the analysis has finished. We have some results, and I'll show you what the plots look like. It's it's a similar trend as we saw before. We have a lot more points, but the point is, it was completely effortless to just run this as a parametric study on more points. And what I'm doing on top of this, but I haven't, at the time of recording this, I haven't finished yet, and it's not in a publishable state, but I'm wrapping this around in a library so that you can just theoretically just write your FreeCAD model and then run a multidimensional parametric analysis, so you can specify more than one constraint. You can have a little bit more fine control over stuff like how what parameters you get out, have a bit more control over if you want to plug in your own calculations to say if you want to do a fatigue criterion where you need maybe the principal stresses and recombine them in certain ways. So that's in progress, but if you subscribe to my channel, I will be updating you on when the library comes out, and I'll put out a new video soon doing a at two-dimensional parametric analysis as well. So for now, thanks for watching, and I hope this was useful to you. And if it was, let me know, drop me a message, and it'll be great to talk to you. Thanks.